Hello everyone, our paper is Improving Resource Utilization by Timely Fine-Grained Scheduling. The core problem we're solving is to improve cluster resource utilization, which we break down into scheduling efficiency, or SE in short, and utilization efficiency, UE. We focus on workloads that consist of many OLAP, machine learning, and graph analytics jobs, as we found common patterns of frequent fluctuation in CPU and network utilization in such jobs. Particularly, CPU is consistently underutilized in short time slices from sub-seconds to seconds, which result in no utilization efficiency. Such dynamic patterns pose significant challenges on existing container-based scheduler designs. To address the problem of dynamic resource utilization, we designed EuroSys that achieves high SE and UE by fine-grained, dynamic, load-balanced resource negotiation. We have 4 design objectives. First, the execution framework should calculate each type of resource need, such as CPU, network, and memory at runtime, so as to request resources from the scheduler accurately. Second, the execution framework should only request and obtain resources when they are needed, and resources should be released immediately when it is not used. These 2 objectives guarantee high UE. The following 2 objectives are built upon the first 2 and solve for high SE. The scheduling framework should schedule jobs and tasks in a way such that several nodes in the cluster have balanced load. Finally, we want to achieve low latency. To achieve the design objectives, we borrow the notion of monotask and design a new mechanism. Monotask is a unit of work that uses only a single type of resource, such as CPU, network bandwidth, disk I/O. It was originally introduced by Osterwald and others at SOSP 17 for job performance reasoning. In our work, we use monotask as a basic unit for both scheduling and execution. In existing work, scheduling is based on the container abstraction, which is a bundle of computing resources, and treats the underlying execution as a black box. In contrast, the execution framework manages tasks in the data flow, which do not have explicit annotation of resource usage. EuroSys integrates scheduling as an execution runtime and provides a simple set of primitives to construct a data flow. CPU, network, and disk operations can be specified in an operation graph by the function createOP with a corresponding resource type. The operation dependencies follow the data dependency in the data flow. The operation graph will be transformed into an execution graph at runtime, where each operation is transformed into a set of monotasks, and each monotask works on one dataset partition. Monotasks with narrow dependency form a task. This is the system architecture. With monotask-based resource request and release, we attain high UE. Upon that, by distributed queue design and the load-balanced task placement strategy, we attain high SE. Our task placement strategy differs from existing strategies in 3 key aspects. First, we design a unified measure for multidimensional resource consumption and place tasks to maintain per-resource load balancing among workers. Second, to handle workloads with dynamic resource utilization, we use the total resource consumption in making placement decisions, in contrast to peak demands of tasks. Third, our task placement strategy is stage-aware, which avoids stragglers created due to scheduling delay. There are more scheduling details in the paper. We show by experiments that our design objectives are achieved in EuroSys, which result in high utilization of the bottleneck resource. In conclusion, EuroSys is a framework for both resource scheduling and job execution. It handles jobs with frequent fluctuations in resource utilization. By capturing dynamic resource needs at runtime and enabling fine-grained, timely scheduling, EuroSys achieves high resource utilization, which is translated into significantly improved makespan and average JCT. Thank you for listening, and feel free to contact me if you have any questions.